Hello friends, in this video I will show you how to generate a sinusoidal signal using Matlab. We have two cases, one is a discrete time case and another one is a continuous time case. So let's generate a sinusoidal signal in discrete time case first. For that we want to define the independent variable first. Here the independent variable is discrete time instances. Let's define it as vector n with the minimum value -10 has a spacing of 1 and maximum value 10. Next we want to define the amplitude. A sinusoidal signal in a discrete time case is represented as x of n is equal to a sine capital omega n plus phi or a cos capital omega n plus phi, where a is the amplitude, capital omega is the angular frequency and phi is the phase angle in radians. So let's define it as x underscore n is equal to sine of n. For producing a sinusoidal signal in a Matlab, we use the function sin sin itself. Next, we want to plot the discrete time signal. In order to plot the discrete time signal, we use the Matlab command stem. Here the x-axis is discrete time instances n and y-axis is x underscore n. Next, let's give a title to the graph as sinusoidal signal in discrete time. Next, x label as n, y label as amplitude, and next we want to define the range of axis. Minimum value of x-axis is -10, maximum value is 10. Minimum value of y-axis is -3, maximum value is 3. So let's run the code and observe how the graph will look like. So the sinusoidal signal in a discrete time domain will look like this. It will plot t of -10, t of -9, t of -8 up to t of 10. The time period between these two instances is known as a sampling period. Let's decrease the sampling period and look how the graph will look like. For that I am going to change this 1 to 0.5 and run the code. Now let's observe how the graph will look like if we decrease the sampling period. Now we get more number of points and now it will look like a sine wave. Okay, this sinusoidal signal has an amplitude of 1, angular frequency of unity and phase angle is 0. Let's produce 4 different sinusoidal signals and observe how amplitude, phase angle and angular frequency will affect the signal. For that I am going to copy paste this program 4 times. Defining x1 is equal to sine of n. In previous case, same as that of the previous case, here x1, this as x2 and multiplying this signal with 2. Now the amplitude of this signal becomes 2. Then changing the name of the title of the graph to change in amplitude. Now defining this as x3 and giving a angular frequency of pi by 2, making this as x3 and changing the title to change in angular frequency, changing this to x4 underscore n is equal to sin n plus pi by 2 radians, changing these to x4 and changing the title to change in phase angle. For getting the graph, four graphs in a single window, let's define the function subplot. In this, subplot of number of rows is 2, number of columns is 2, and priority of this graph is 1. Next here, so here the priority is 2. Copy pasting it here, and here the priority is 3. Here the priority is 4. Now let's run the code and observe how the four graphs will look like. So this is how the initial standard sinusoidal signal in a discrete time will look like as in the previous case, but a change in amplitude is seen in this graph. That is, the amplitude is increased from initially there is a 1, it is 1, now it is increased to 2. So the amplitude, this is how the amplitude will affect the signal. And the change in angular frequency, when we change angular frequency here, the when I increase the angular frequency here, the time period will decreases. Time period, that is the time taken for completing one complete cycle, decreases. This is how the signal will look like when it undergoes a change in phase angle. When phase angle changes, the signal undergoes a phase shift. Here also you can see a phase shift, but in case of change in amplitude, the phase of the signal doesn't changes. But okay, but in other two cases, it will change the it will make a phase shift in the signal. This is how amplitude, angular frequency, and phase angle affect the sinusoidal signal. Next, let's produce the sinusoidal signal in continuous time domain. The generation of sinusoidal signal in continuous time domain is similar to that of the generation of sinusoidal signal in a discrete time domain. But the difference is that here the spacing of the x-axis is to be reduced, and you want to use plot command instead of stem command. So let's define the independent variable as a vector t whose value varies from -10 with a spacing of 0.1 to 10. The representation of a sinusoidal signal in continuous time domain is x of t is equal to a sine omega t plus phi or a cos small omega t plus phi, where a is the amplitude, omega is the angular frequency in radians per second, and phi is the uh, phase angle in radians. So let's define it as x underscore t is equal to sine of t. In order to generate the sinusoidal signal in continuous time domain, we use the function plot. X-axis is t and y-axis is x underscore t. Then let's give the title as sinusoidal signal in continuous time. Next x label as t and y label as amplitude. Next we can define the region of axis. X-axis varies from -10 to 10 and y-axis varies from -3 to 3. Now let's run the code and look how the graph will look like. So this is how the sinusoidal signal in continuous time signal will look like and how it has to be produced. Here you can see that in the signal has an amplitude of 1, angular frequency is unity, and phase angle is 0. Another way to represent a sinusoidal signal is x of t is equal to a cos omega t plus phi. Let's define that also. Let's define x2 underscore t is equal to cos of t. Let's change these to x1 of t, and I am going to plot the two functions in the same graph. The syntax for that is plot x1 y1 then x2 y2. Here the x-axis is represented by time and y-axis is represented by x1 of t, and in the second case it is x-axis is time and y-axis is x2 underscore t. Here I use another function known as legend. I will show you why I use this function after running the code. So now let's run the code and observe how the graph will look like. So here we will get the cosine representation and sine representation of the sinusoidal signal. I use the function or command legend in order to get these things. That is the here the blue represent x1 of t and red represent x2 of t. That is x1 of t. In the command we have defined x1 of t as a sin t and x2 of t as cos t. So in the graph we will get x1 of t. That is the sine function. This is a cosine function. Then let's see what is the relationship between sine and cosine function. Here I am going to give a phase shift of plus pi by 2, and when I run it, you can here see that the x1 of t is under x2 of t. That why it is not visible here. For understanding, I will increase the amplitude of x1 of t. Then you can see that initially it was not there because it is under x2 of t. Now I increase the amplitude, you can see x1 of t and x2 of t. From this we can conclude that sine of t plus pi by 2 is equal to cos of t. That you know. Next let's do the time reversal on the cosine function. For that I convert this function to uh, cosine function. x1 of t is equal to cos t and s2 of t is equal to cos minus t. When we run the simulation, when we run the command, we get the signal. That is here the x1 of t is under x2 of t. That's why we can't see it. From this we can conclude that when we subjected a cosine function in time reversal, we get the cosine function itself. That is cos of minus x is equal to cos x. Its mirror image is same as its original signal. But in case of sine signal, this is not the case. This is the x1 of t, that is the sine of t, and x2 of t, that is the sine of minus t, is the red one. Here you can see what happens to sine signal when it is subjected to time reversal. That's why sine is an odd function and cosine is an even function. Cos of minus x is equal to cos x and sine of minus x is equal to minus sine x. Now let's do signal addition operation and get its graph. For that x1 underscore t is equal to sine of t and x2 underscore t is equal to cos of t. Let's define x3 underscore t is equal to x1 underscore t plus x2 underscore t, and in a plot function let's include x3 underscore t also. Legends function also let's include its name as x3 underscore t. Now let's run this code and obtain the graph. So we will get the graph like this. x1 of t is sine, x2 of t is cos of t, sine of t, cos of t, then it's summation. Sine of t plus cos of t is this yellow colored graph. Blue colored graph is sine of t, red colored graph is cos of t, and yellow colored graph is uh, sine of t plus cos of t. So you can do signal addition in this way. Then let's do signal multiplication. For that we can change this plus operator to multiplication. Remember to put a dot before multiplication, because here we are using the scalar elementary multiplication. Otherwise it will do the matrix multiplication. So let's get it like this. This blue represents sine of t, red graph represents cos of t, and it's a product. This yellow is its product. In this way we can do signal multiplication. So in the production of sinusoidal signal in discrete time case, the spacing on the x-axis is more when compared to the spacing on a x-axis in case of continuous time signal. And here you use the function or command stem to produce the discrete time signal. Here you use plot for getting the sinusoidal signal in continuous time case. Sinusoidal signal in discrete time case will look like this, and sinusoidal signal in continuous time case will look like this. Hope you understand the generation of sinusoidal signal in discrete time and in continuous time. Thank you for watching this video.